Behind every force in nature, there lies a mathematical story. At the heart of gravity, electrostatics, and even heat flow, there is one equation, the Poisson equation, a timeless principle that connects the source of physical phenomena to the shape of the field it creates. In this video, we are going to learn Poisson equations, which is not just understanding the mathematics, but it is discovering how nature reveals itself through equations. My name is Shaunak and you're watching this video on my channel, Physics for Students. Welcome to this fresh new video in learning what is Poisson's equation. Well, as usual, first let us look in understanding what is this Poisson equation all about. But before we go ahead, I would like to give you first a rather intuitive understanding before going into the mathematics. Well, Poisson equation is I would say a partial differential equation that appears in many branches of physics, especially in thermodynamics, gravitation, and various other areas. If you go by the mathematical formulation of this equation, it looks like this or this or this. We will look in why these are different formats, and we take one format to go ahead. Now, I would like to make you imagine Poisson equation something like a kind of a bridge. Well, what does a bridge do? A bridge connects at two ends. Here also the bridge connects two ends. One is the source, which causes the root of any physical phenomena, and the second one is the potential, which is basically the effect of that. So if you consider that the source or the root cause is mass density, then the effect is basically it creates a gravitational potential. If there is a charge density, it would create electric potential. If there is a heat distribution, then it would create a kind of a temperature distribution, and so on. For example, quantum mechanics, etc., which I have not mentioned. So from here, what we can understand that there should be a kind of a physical phenomena, which it can be, for example, it can be gravity, and this can basically lead to a source which is a mass density, and the potential which is denoted by F is the gravitational potential. Similarly, there can be electrostatics physical phenomena which leads to charge density and which leads to electric potential. Also in electrostatics in physical phenomena, there can be heat source density which causes a potential which is called the temperature. So we see there are three physical things. One is a physical phenomena which is meant by a source, and there is a potential which is F, and all these three phenomena actually pertains to what is called the Poisson equation. So if I now take a little bit a strict formal rigorous definition, then we can say that Poisson equation serves as a fundamental mathematical framework how various physical phenomena emerge from the interaction, and this interaction is between a source and the corresponding potential field. If I go by the mathematical symbol, it looks something like this, where I would say this inverted triangle, which is called, I will talk to that where it originated. This is basically a vector operation. You can say that it contains certain amount of partial derivatives, and then we have got a F which may present the potential, which is a scalar function describing its underlying structure, and then we have got a phi which actually denotes something which is called a source distribution. You can think of something which is quantifying the physical quantity responsible for generating the potential, such as we have seen mass density, gravity, charge density, electrostatics, and so on. So from this entire equation and what we have learned so far, what we can tell is that there is a source. This source acts as a fundamental cause of the phenomena. It represents physical quantity that generates the field. Then there is something which is called the spatial variation, that is the potential. So the potential is an abstract scalar function that encodes how I would say source influences the surrounding space. And then we have something which generates a field. We can say that these are observable force field in the system, which is derived by taking the gradient of the potential on a very technical front. Now, in order to give you a better visualization of actually what Poisson equation does, because we have not got into understanding each and every notations of this, which we will do, I would like to tell you that Poisson equation basically provides a kind of a unified framework. We have just seen a bridge, so you can imagine that the bridge actually is connected for the describing how the physical systems respond to the other sources. Now you can start imagining placing a heavy ball on a stretched rubber sheet, and you get this equation. For example, this heavy ball represents the source, which we have just seen in the Poisson equation as phi, which is the mass density and how much mass is concentrated here. This red line which runs through this is the rubber sheet, presents the space and the dent it creates due to the potential field. We can call it as nabla square F. And this one, which actually cause the bending of the sheet, the deeper the dent, the stronger for the gravitational potential at that point. So what we can say is that the heavy ball represents a source, which is the mass density, how much concentrated it is. The deeper the dent, the stronger the gravitational potential at the point, and the rubber sheet represents the space and that it dents and creates the potential field. So from here what we can say is that more heavier is the object, the deeper is the curvature. So the equation tells us wherever the ball's mass is placed, the rubber sheet or the space curves around it, and the heavier or more mass density, the steeper and deeper is the curvature. So mass bends space, and the Poisson equation shows how much bending happens at each and every point. Now we go to the equation of the Poisson equation. Now this is the nabla squared F. This actually shows how the field is curved. We have just seen with an analogy of a rubber sheet. And this phi is actually what is curving the field. I mean to say the source. And the most important thing is this equal to. It balances the cause and the effect. You can say this is a kind of a bridge. The amount of bending in space is exactly equal to the source that is bending it. So we can say that the left side actually tells how the field is curved by space, and the right side is what is curving the field, the source, and the Poisson equation is telling that space bends where there is mass or charge. So we can say that the Poisson equation is the language of the universe that describes how matter or charge or energy bend the geometry of space itself. Now, have you noticed there is something very similar when we talk of this Poisson equation and make it zero, and it becomes an empty space, the Laplace equation turns to be zero. Now, as we have said that the source is something which actually denotes the geometry, and the left hand side is the geometry and right hand side is the source. So the field is curved while its right side reveals what it is curving. So we get a similar kind of an analogy with Einstein field equations, where the left hand side of the equation is the geometry and the right hand side is the source, that is the stress energy momentum tensor. So in all ways if you know further, that you will see that the Poisson equation at our Einstein field equation at low gravity, low source and low density reduces to what is called the Poisson equation or the Newtonian Poisson equation. But there is a big but. Now whatever we are looking till now is a very generic form of Poisson equation. It doesn't contain any specific, but at this moment it is a good time to look and understand what are the other forms in which the Poisson equation can be taken. Remember that the Poisson equation is a tool which actually helps us to calculate certain physical phenomena and complexities when we use that in physics. So if you take this one, this is the Poisson equation used typically in understanding the Newtonian gravity. And as you can see, this one is basically the Laplacian operator. Don't worry if you don't understand Laplacian. I will be covering this part in the video. This phi is basically what is called the gravitational potential. Then there is a capital G, which you can understand is the gravitational constant of Newton. And then we have got something which is a rho, which calls the mass density. That means the mass which is stored in per unit, the density per unit mass. And this negative sign is truly important because it shows that gravity is always attractive. It always pulls and never pushes. But remember, this is as far as Newtonian gravity is considered, because there will be exceptions in terms of general relativity. So the left side of the equation describes the curvature of the gravitational field, and the right side describes the source of the gravitational field. And this actually brings us to certain good conclusions. It relates the gravitational potential to the mass density. Where there is mass, there is obviously gravitational field, and in simple terms, where there is more mass, the gravitational field is more curved. And as I told you, in weak gravitational field and low densities, Einstein's field equations reduce to what is known as the Poisson equation. Now this is as far as the Poisson equation used in gravity is concerned. Now what about this one, Poisson equation used in electrostatic? That is also very remarkable. Now here you can see this V is basically the electrical potential, and over here this part of the equation shows, it actually shows that this term nabla square V, which is a Laplacian of the electric potential, it describes how the electric field or the potential changes in space. So if it is a non-zero, it indicates that the potential is not uniform and it is curved. Now this sign, you know, it is a charge density. It represents the amount of electric charge per unit volume at a given point and is the source of electric field. Permittivity in free space, and this is also known as the vacuum permittivity. And this sign, this negative sign, it is very crucial. And what it does is that it indicates that the positive charge density creates a negative curvature in the electric potential. So a positive charge density creates what is called a negative curvature in the electric potential. And that is the reason you will see that in case of a positive charge, so as the charge density, you will see that in electric field always points from higher to lower potential. So that is why electric fields go outwards from positive charges and inwards towards negative charges. So here you can see that the field lines are going from the positive charges outwards, and for the negative charges it goes inwards. So the negative sign actually ensures that positive charge actually creates attractive, I would say, potentials. So this is super important. Here you can see that the field lines are spreading. Why electric fields go outward from positive charges and inwards? So very important point for you to remember is that the negative sign ensures that positive charges create attractive potentials. Further, what we can see is that this part of the equation, it also tells if there is a charge, more charge at a point, the potential will bend, and in certain cases it will bend more steeply, and so on. So from here we can see that on the entire left hand side of the equation, it tells the spatial variation. It is the same as the gravity, but only it is in case of electrostatic. So in case of this, it tells you that how the electric potential spread out in every discrete, I would say, direction around a point. So from here what we can understand is that what this equation tells is that it establishes a relationship between the electric potential and the charge density. And the charge density acts as the source that creates the electric potential. And as you can see, we will cover this later, but just to tell you, this Laplacian operator, this one describes how electric potential is curved or distributed in space due to the presence of charge density. So obviously there is a charge density, that is why the electric potential is distributed. Where there is wherever there is a charge density, the electric potential will be curved. Now what if we apply Poisson equation in case of fluid mechanics? So here the equation looks something like this. This is the same Laplacian operator. This is the pressure field like air pressure or water, and this is the density of the fluid, whatever fluid you're considering. So this negative sign, again, this is typically very important, indicates that the region of higher density creates a negative curvature in the pressure field. Now this is something which you need to note, that in electrostatics what we found is that the source compresses the space, higher density makes pressure drop around it. So that is why I give this nice kind of an animation, that the source actually, the higher the source, it actually pushes, higher density makes pressure drop around it. This is for, in case of fluid mechanics. Now, similarly, if you go back to the electrostatics, you will see that the source pushes fields away. Here it is compressing, it is just the opposite. The source pushes field away, potential drops near positive charge because like charges repel, if you remember, obviously. Now from here what we do is that this negative sign is doing here is that this rho, that is the density of the fluid, is greater than 0, then there is more mass or heat and the pressure goes down like this, like a dent. And if rho is less than 0, then there is less mass, or I would say cold region, and in this case the pressure rises up just like a bump. So this part of the equation, which we have seen earlier in electrostatics, here you can see that this minus sign, positive charge just pushes the field outwards. It is repulsive, so this is why the lines go out. So here's a stark difference. In fluid mechanics, the source compresses, whereas in electrostatic, the source pushes the fields away, and that is why potentials drops near positive charges, and that is why like charges repel. So from here what we can understand that we have seen the different form of Poisson equation. One is that we have seen that for gravity, and gravity tells that mass curves space-time. We have also seen for electrostatics, which tells that charge creates variation in electric potential. We have seen fluid pressure, the density compresses pressure fluids, and we have seen temperature, where how it creates gradients in temperature. So overall for all these equations, one thing is common, that is the left hand side will always describe how the field is curved and the right hand side will always describe what causes the curvature. And overall we can say that the Poisson equation describes how the presence of source induces a kind of a spatial variation in the surrounding potential field. Now till now we have dealt a lot of this inverted triangle squared, but I have not explained it. So here comes, what is this inverted nabla squared? Now this is coming from the Greek letter nabla, which is a triangular symbol representing an inverted Greek delta. So the nabla actually comes from the reason from the Hellenistic Greek word this one, which actually recalls us of a Phoenician harp. So you see the harp is an inverted triangle and it is the same. So what it shows is that the harp, the instrument after which the nabla symbol has been named. Now we have to remember one thing, this nabla is basically what is called a differential operator. Now differential operator, why? Because it acts on scalar fields, vector fields or other mathematical objects to produce different types of derivatives, and that is the reason it is called a differential operator, because it performs certain differentiation. We can think of that. Now we can think of this nabla vector which contains, we can say it is just this nabla is a vector that contains partial derivatives d by dx, d by dy and d by dz. Now each one of these actually measure how quickly certain quantity changes over a small distance in the x direction, y direction and the z direction. And you can just imagine this to be a kind of a hill, and if the road is steeply uphill, then del f by del x would be largely positive. Field value is increasing. If you're on a flat road, then del f by del x is 0 because no change at all. And if there is downhill, then del f by del x is negative because the field value is increasing. But hold on, I have just told you that these are del f by del x, and we have written df by dx. So where is the problem? No, there is no such problem. I'm just first of all explaining you what is an ordinary derivative, and then I will come to this partial derivative. So in order to do a better visualization, I will like to take an example, a thought experiment. Think of it that there is a kind of a sugar packet and you squish open this sugar where the lot of sugar are spilled apart. Something like this, and then we try to plot a graph which shows the sugar distribution. So as you can see, the sugar distribution graph look like this. So lots of sugar at the origin, and there is less and less as we get away from the origin on either of the direction. Now if we mention our sugar distribution is leveled as f, for example, this one, then df by dx, actually it simply measures how quickly the sugar distribution changes as we move in the x direction, and df by dy also measures the same thing, how quickly the sugar distribution changes in the y direction. So we can think it as measuring the gradient or the slope of the sugar distribution, where the curve goes like this. So here, for example, the gradient is so steep, so our sugar distribution drops off quickly, whereas the other areas, something like this, the sugar distribution not so steep, so the sugar distribution is not changing and the amount is more or less a little bit less. Now we can use this nabla operator, or what we have seen, this inverted triangle operator, into our sugar distribution, and what we get is this. Except you see that there are curly D's. And what do we mean by these curly D's? Now, if we find that the sugar distribution of that what we have got does not even change over the x-axis, but also changes in other direction, for example, y and z, and the change looks something different like this. So we understand that the curly D's are measuring the change of our sugar distribution in the x direction, while assuming that the sugar distribution remains constant in other direction, and del f by del y also measures the gradient or the sugar distribution in the y direction, while keeping for example y and z, x and z, it should be anyway, is constant in other direction. So what we can think of this as, we can think of curly D's as isolating or separating, changing in one direction of x and y and z without worrying about any other directions. So these are called partial derivatives. Those you know already about partial derivative. It focuses on one direction at a time, pretending the other directions are constant. Now, why we are at all, worried about partial derivative? Because Poisson equation contains a lot of partial derivatives. Now, in Poisson equation, what you will also see that we have got a del squared. And this del squared is basically a dot product between two vectors, del dot del. And if you're aware about divergence, gradient and curl, so here it is the dot product between two del vectors. So if you're aware about divergence, gradient and curl, we are trying to find out what is called the divergence of the gradient of some quantity. So the first one is the divergence, second one is the gradients. And I would like to recall a very important concept, that the dot product of the scalar or the scalar product between two vectors is given by multiplying the corresponding components. So if you have got two vectors, we multiply the components of these two vectors and then we add up all these vectors. So we do the same thing when we are trying to find out what we call the dot product between two del vectors. So we do the same thing, but in case you see that except we do not multiply, what we do is that we apply a derivative over a partial derivative. And those who are aware about vector calculus and partial derivatives, we can write it just as we have done this one. Let me show you. This page shows that we are adding up the dot product. So here also we have taken the dot product, we have added up the partial derivatives, and just like any normal vector, and those who know about partial derivative, we can write as this one, which is called the second derivative in the x and y and z direction of the function f. Or more neatly, I can take f common and we write something like this. So this is what the Poisson equation's partial derivatives look like. But the question is that, is there any name for this one, the inverted triangle square? Well, I know you have noticed this one in this video where I talked about. Now this is what is called a Laplacian. I will try to explain Laplacian in a very easy and pictorial diagram. So if I take by the definition, the Laplacian is simply the dot product of two nabla vectors. I would say two nabla operating on a acting field. So here you can see this one in vector calculus. This is what is called the divergence. So here you see in the mathematics, the Laplacian operator is a differential operator which is given by the divergence of the gradient of a scalar function. Don't worry, I will going to explain you what is divergence, what is a scalar function. Now, as you can see that this can be written as this, divergence of the gradient of the function f, div grad f. So in vector calculus, if you are worrying about divergence, then this is what is called a positive divergence. When divergence is positive, the vector field is spreading out from the point like a water flowing through a source, for example, air flowing out of fan. This is called a positive divergence. For negative divergence, when divergence fields are converging vector fields into the point, this is called what is called a negative divergence, something getting sucked in. And when there is, I would say, zero divergence, the amount of flow entering and leaving the point is all equal. So this is known as the zero divergence. So in short, so what we can tell is that this Laplacian, the nabla f, which is the gradient, this tells actually how quickly the field changes. That means the first derivative that you have seen. And when we take the Laplacian, nabla f, this takes the divergence of the gradient, which is basically measuring how much the field bends or curves at each point. That is the second derivative. So the first derivative is telling us how quickly the field is changing, the divergence, and then we are taking the nabla f. This takes the divergence of the gradient. There is divergence, and then we are measuring the gradient, which is basically measuring how much the field bends that is the second derivative. So all in all, we can say that Laplacian actually tells us how much the field at a point is different from its surroundings. To give you a better idea, let us go into a kind of a thought experiment. We have seen what is a gradient, we have seen what is a divergence. Now we will understand what is called the divergence of the gradient. I want you to imagine a room which is filled with air, and each of these air are flowing possibly in this direction. So for example, we mention it as three-dimension f, x, y, z, temperature at each point. And when we take the gradient, I am meant to say in which direction the temperature is riding, left, right, or either way. And the divergence of the gradient. So this is the gradient, in which direction the temperature is riding. But when the divergence of the gradient, we're trying to tell how much heat is piling up or escaping at every point. So the arrows of the gradient are pointing away from you in all directions. To give you a better idea, imagine that of a hill and you're standing right in here and you can see these arrows are pointing out. So what we mean by this is that the arrows are pointing away from you in all directions. So the divergence is positive. Nature is saying something is pushing out from here. For example, if you take a hot iron ball or a positive electric charge, I will just explain to you. And that is the reason for positive divergence. You see the electric field lines are going away. This is a kind of an analogy. If you take the same kind of a hill analogy, and here you see the arrows are pointing towards you. Here it is towards you from all sides. So the divergence is negative. And nature is saying that something is sucking away everything in. And when you're standing over here, so here you can see it's sucking away the negative divergence. So over here, you can see where there is no divergence, the land is perfectly flat. The land is perfectly flat. So what we can say from here, so this one, the nabla f is the gradient, how fast, and the nabla dot is the divergence, how much something is spreading out from a point. So first tells how fast, and then the second one tells how much. There's an important interpretation in this aspect is that this Laplacian equation, the field is flat and there is no source. And whenever there is a value, the field is curved by some source. So this is actually the generic Poisson equation which we have been looking. So when we are talking of heat, which would be a good analogy, so I want you to imagine this one, which is a kind of a source, and you see that the lines are pushing out. So the field is spreading out. The point is surrounded by higher values. Heat or mass is flowing out. It is a kind of a valley-like structure. So it is a positive divergence, and the Laplacian is greater than zero. Now when you get some kind of an ice cube which is melting, the field is pulling in. The point is surrounded by lower values. Heat or mass is flowing in. It is a hilltop-like structure. This is a negative divergence. And when there is nothing happening, net flow of the field, equilibrium, flat surface, neither valley nor a hill. That is why the Laplacian is greater than zero. So you need to ask yourself that is something spreading out a source? Is something squeezing, or is everything in balance? So positive divergence is like standing inside a valley where everything is trying to run away from you. Negative divergence is standing on a hilltop where everything is trying to pull within you, and where there is no divergence, the landscape is perfectly flat. So we understand from here that the divergence of a gradient is a measure of how much the steepest change of field. We first measure the gradient, that means in which way it is going, and then how much the field is spreading out. And the Laplacian is nothing but the second order differential operator, the first being the gradient, the second being the what we call is the divergence. So the net curvature or spatial variation of a scalar field represents how much field at a point differs from around it. Now, we have seen the overall idea of this Laplacian, but we have looked in a very generic form of the Poisson equation. Nothing very specific, nothing intuitive, nothing physical. But now I would like to show you this equation. This would give you the Poisson equation, a proper physical format. But remember, we are going to replace this phi with the capital V. The reason will follow. And this last equation at the bottom is known as Gauss's law for gravity. Now, Gauss's law for gravity, why we are learning? Because it has got a profound implication in order to understand what is called the Poisson equation. Now, the Gauss's law for gravity has got again different forms. I'm just going to show you, although we will take only one form. It might look like this or this or this. However, we are going to concentrate on this part. First of all, I will take, this is the integral form of Gauss's law. However, there's a differential form which we will look later. Now, first we will try to concentrate on here. This is the integral sign with a circle indicating that the surface is closed. So S is basically a closed surface, and it shows that the total gravitational flux through the surface or the entire closed surface S. That means it measures how much gravitational field is flowing out from the enclosed mass. Then we come to this G. It is the gravitational field which represents the gravitational acceleration of each point in space due to mass distribution. It is a vector field. Then we come to something which is called a dA. We will plot on that. Now this is what is called the infinitesimal small area. So the magnitude of dA is the small surface area dA, the direction, and it symbolizes infinitesimal vector area element which is closed within the surface S. Next we come to something which is very important, which is the minus sign, and it says that gravity always pulls masses inward, never pushes them away, only through a Newtonian gravity. Then we come to this 4 pi, which is a kind of a constant. It arises from the spherical symmetry of spheres. G is the gravitational constant and m is the enclosed mass. So from here what we get is this one. This part of the equation actually tells that the integral sign indicates that the surface is closed, and the total gravitational flux to the entire surface S. It is a measure how much gravitational field is flowing out. And this is important. G dot dA, this dot product gives the flux of the gravitational field through the surface element. Physically, the quantity represents how much gravitational field passes through the infinitesimal small surface area. So all in all, what we can say is that the Gauss's law for gravitation states that the total gravitational flux through any closed surface is proportional to the total mass enclosed within that surface. Now, here is something very intuitive. We all know that the Earth's gravitational field looks something like this: radially inward pointing gravitational fields. And what does it mean? That if we place a mass somehow on those gravitational points, then any mass placed over here at any one of those points will accelerate downwards to the center of the Earth, something like this. Now my question is that how do we know that? And this is where Gauss's law come in. Now for this we have to consider a random surface. For example, we can take that of an Earth, and here we will take a closed surface or a randomly closed surface that entirely encapsulates the Earth. It's a closed surface. So let us consider sphere, and then we break this sphere up into this tiny small pieces, and each one of them has got an area which is called a dA. Now importantly, we also represent this surface with a vector, which is something, this surface I have magnified. It's got a vector which is this one, dA. Now why we are doing? Because this vector is perpendicular, as you can see, to the surface or the surfaces, multiple surfaces. So instead of surfaces, we have to deal with just one vector, and the size of the vector corresponds to the area of the surface. So this gives us an advantage of representing the surface with just one single vector rather than the entire surface. And that is why the mathematical definition looks like this. So the size of the vector gives us the size of the area, and this, because it is perpendicular, the direction, we are considering one single vector, which gives us a better kind of an idea. So this a picture will give you a better idea in order to find the dot product. Here are these surfaces, and we got this G which is pointing downwards, which is the gravitational field, and we have got the vector area which is pointing up. Now the question is that in order to find this G dot dA, I mean to say we are trying to find the dot product, how well the gravitational field, so the dot products actually of two vectors, they actually show that how the two vectors actually align with each other. In this case, they align with the area vector, or how much the gravitational field lines pass through each element. So we find the dot product. If they're pointing in the same direction, then obviously they have got a maximum. If they're perpendicular, then it is equal to 0. So we find the dot product. So this picture, same one, we find the dot product of this area. So here it is, how will the gravitational fields lines align with the area vector? That is what we are trying to find. So what we do is that we actually we try to find out those little G dot dA, right? G dot dA and plus D dot dA and G dot dA. It is what is going on, and then we add up all those contributions, something like this, and it goes on. And this is what the integral sign says. It adds up those little contributions, and the sum of the closed surface is equal to minus 4 pi gm. 4 pi gm, where we would consider m as the mass of the enclosed surface and the mass of the earth. In this case, it is an example. Now here I have shown you a but. The reason is that finding a solution for Gauss's law of gravity is a little bit intimidating. I mean to say is a little bit complex. The reason is this one. The Gauss's law for which we have seen in a kind of a finding a solution is complex, because this includes a lot of symmetry and mass distribution and boundary conditions. Now the real challenge is that it is not just a simple integral equation, it is a differential equation, and it's not a simple algebraic equation, it is a partial differential equation. Now you might ask me, why is it difficult? Because it is PDEs and it contains what is called nonlinear nature of gravity. So a lot of issues regarding the mass, charge, density comes up. So the question is that when it is difficult when there is a irregular mass distribution, when there are multiple masses, and how to solve it in curved space-time, because in general relativity it becomes difficult. So it becomes easy when we are taking spherical symmetry, for example a planet or a star, cylindrical symmetry, an infinite wire, and irregular masses or plane surfaces. So these are the issues which we come up. So finding a solution becomes difficult. But in spite of those difficulties, we find something very quick, very easy, very intuitive. And that leads us to this part of our video, Poisson equation for Newtonian gravity. And the Poisson equation for Newtonian gravity tells us that in spite of the difficulties, what we do find is that the gravitational field, this one, along the entire surface must look something like this. I'm not going into the mathematical details of this, but this is how it looks like. So if you take any arbitrary surface also, then also the Earth's gravitational field looks like this. And this is the beauty of Gauss's law. So what we see is that from this part, as you can see, that this negative sign, which I have called as gravity is always attractive, not repulsive, but there is also another reason. The reason for this is that it says that the area or the differential area which you have looked, the vectors are all pointing upwards. Whereas in case of gravitational field of Earth, it points downwards. So it is exactly in the opposite part. So the area elements have outwards out of them, whereas the gravitational fields are exactly opposite. So what we can say is that the Gauss's law of gravitation helps us to find the gravitational field generated by a mass distribution in any arbitrary area by relating the total mass enclosed within region to the divergence of the gravitational field. Now we have seen the integral form of Gauss's law. Now this is the differential form of the Gauss's law. Now why I am showing you the differential form? Because from here we will see the Poisson equation for Newtonian gravity. Now here everything is more or less known, except that here are new two terms, the divergence of which is there, and this one is called the gravitational field. So here the divergence of G is equals to minus 4 G pi G rho. and this one is the mass density, which shows the mass per unit volume. Now, if you see that this looks somehow similar to the Poisson equation. So we have something on the left here, something on the left here, something on the right, and we got some function which is on the right hand side, but the only difference is that we have got the divergence of some vector quantity. Remember, in the earlier equation, that is Gauss's law, and here we got a Laplacian of a scalar function. Now, the gravitational force is always a conservative force. When I say conservative, I mean to say here is the Earth, and it means that if I place a point and try to move this point from here to here or from here to here, the work done by the force to move an object from one point to another depends only on the initial and final position, not on the path taken. So we can say that in simple terms, you move an object in a gravitational field and you bring it back to the starting point, the total work done will always be zero. No energy is lost. Now, this conservation force, which gravitational force is a conservation force, this actually brings to a mathematical understanding, which is called the curl of a vector field. And we know that the gravitational field, the curl of a vector field is always zero. And that also happens in case of a gravitational field. So mathematically, the curl of a vector field checks whether the field has a rotation or a swirling motion or something like that. Fortunately for us, the gravitational field always points radially towards the mass, like arrows going straight into the Earth. There is no swirling, no vortex in motion in the gravitational field. And gravity only pulls, it never twists. So this translates to the fact that the curl of the gravitational field is zero. But remember, again, in Newtonian mechanics, but in case of general relativity, things will be a little bit different. So what does this actually mean? So we get here a mathematical identity in vector calculus where we call the curl of the gradient of the scalar field is always zero. So formal statement for any field, this would be this, and this part is known as the curl. I'm not going to explain in this video what is a curl, but later, and this is something which is called the gradient. So from here, why this is important is because it gives basically the conservative forces like gravity and electrostatic forces comes from a scalar potential. It says that Newtonian gravity has no twisting effect, but this is not true in relativity because in Newtonian gravity, it says that nature never twists a slope unless space-time itself bends. And this is exactly what happens in case of general theory of relativity. Hence, so what we can do is that we got the gradient which gives the steepest ascent of the scalar field, like the slope of a hill, and then we have got a curl. It measures how much the vector field twists or rotates around a point. So from here, what we can do is that definitely we can write as this equals to zero. Why? Because the curl of a gravitational field is zero. So from here, we can write that gravitational field as a gradient of a scalar field, which looks something like this. Remember, we just substituted here V to be a scalar field. So now we go back to Gauss's law and substitute this gradient of V for the gravitational field G. And what we get is something like this. So we get a divergence of the gradient of some scalar field. This one is basically the divergence and the gradients of some scalar field. But remember that this nabla, or I would say, yeah, nabla, or the inverted triangle, del dot det, we can call it del, right? So del dot del is also del squared. So from here we get into this one. This is basically the Poisson equation for gravitation. But remember, this is only for specific cases. But for general form of Poisson equation, this is how it looks like. Just a quick note that we have replaced this V with the gravitational potential, which is not the same as gravitational potential energy. I've already made a very old video which speaks about the gravitational potential and the gravitational potential energy, and I leave up to you. You can dig in and find what is the difference between this, and you can let me know in the comment box. So that's all. It has been a very heavy, I understand, mathematical, lot of concepts coming in this video. So that's all for today's video explaining Poisson equation, Gauss's law, gravity, and a lot. Thank you very much for watching this video. If you like this video, please click on the thumbs up button and click on the subscribe and click on the bell icon to get all the notification from Physics for Students. Also keep an eye on my new channel, General Relativity Explained, where I'm putting up a lot of good and explanatory videos on general relativity, how to learn and stuffs like that. You can always contact contact me at this email ID. Stay tuned with Physics for Students, as I will be bringing more interesting, fun-loving videos, podcasts, and a lot of stuffs which you're going to enjoy. But see you very soon. But till then, may the good Lord be with you.